All right, welcome everyone to the last talk of this year's DRP Turkey program. Before I introduce Anıl, I invite all the participants for a round of applause for the organizers of this year's program and for their hard work. Okay, so without further ado, I want to introduce Anıl. So Anıl is a third-year student in Boğaziçi University. He is also doing a double major in physics, and I believe that he wants to be a physicist after graduating. So with Anıl, we worked on Gröbner Basis and Parametre Continuation Theorem, and Anıl will talk about all of that. So the floor is yours.
Hello, everyone. As Levent introduced, I'm going to talk about Gröbner Basis and Parametre Continuation Theorem. First, I will give some basic objects in the algebraic geometry, then talk about the parameter continuation theorem. For a brief introduction, a monomial is defined as a product of several variables with different exponents, and a polynomial is the sum of those set monomials with different coefficients. And many of you know what an ideal is, but an ideal can be generated by a finite set of polynomials, and those elements of the ideal can be written as the linear sum of those polynomials. And in single variable, division algorithm gives us that f equals to quotient times the divisor plus remainder, and the remainder must have strictly lesser degree than the divisor. This is known as the Euclid's algorithm, but for multiple variables, this is not that simple, and we need a tool to order monomials first. That's why we have lexicographic order. It is analogous to how we order words in a dictionary. Thus, we first need an alphabet. Assume that this alphabet is x1 is greater than x2, and so on. Then lexicographic order is defined as x over alpha is greater than x over beta in the vector difference alpha minus beta. The leftmost non-zero entry is positive. And lexicographic order satisfies that it is a total ordering relation. It is compatible with multiplication, and it is a well-ordering. For example, look at these two monomials. First one has x squared, second one has x. If we choose x is greater than y greater than z, then the first monomial is greater than the second one. So when we have a monomial order, a lexicographic order, we have a division algorithm. It is defined as follows. If you have a polynomial f, a monomial order, and the polynomial set, also we denote a monomial in a polynomial, the greatest monomial, the leading term with respect to the monomial order. Then the division algorithm is defined like this, with remainder must not be divisible by any of the leading terms in the division set. R is called the remainder, and it can be denoted like this. However, this definition gives several problems. First, if you change the order of division, the remainder may not be unique. And the main purpose of the division algorithm is to check if f is an ideal. And if R is not zero, we can't check always if f is in the ideal. So we need another object, which is the Gröbner basis, which is defined as let this be a monomial order in the polynomial ring, and let I be an ideal. Then there is this finite collection of polynomials G, which is a Gröbner basis for I if for every element in I, the leading term is divisible by the leading term in some polynomial in the Gröbner basis. What this does for us, if R is not zero, then R is not in the ideal. And if R is in the ideal, then it can be divided by some of the polynomials in G. Thus, by the definition of the Gröbner basis, every remainder in the Gröbner basis must be unique. Gröbner bases are great tools from division to solution of polynomial systems, but they are rather hard to calculate and nigh impossible done by hand. But how do we calculate them? So we need the Buchberger's algorithm. Oh, sorry. Buchberger came up with this algorithm. So first we need to know what an S polynomial is. S polynomial's definition is as follows, but the main idea with the S polynomial is that given two polynomials, when you take their S polynomial, you get a lesser leading term. So using S polynomials and Buchberg's algorithm, we can find the Gröbner basis for an ideal. Let's say F generates the set ideal, and you want to find the Gröbner basis for it. First, you say let G equal to F. Then you check every pair in G and calculate their S polynomials and calculate that S polynomials' remainder with respect to G. Then if the remainders are not zero, then you add all the remainders to the Gröbner basis. Then you repeat again for the steps 2 and 3 with the added remainders until you get for every pair in the new set, every S polynomials' remainder equal to 0. Then you can say G is a Gröbner basis for I. Then, since this is about algebraic geometry, the geometrical counterpart for ideals are their varieties. What an affine variety is that it's the point which solves a polynomial system. Since every polynomial in a polynomial system can generate an ideal, you can define a variety of an ideal, which is defined for every point in the variety and every polynomial in the ideal. Every polynomial goes to 0 for every point in the variety. Likewise, you can construct an ideal from a variety. Say you have a variety with points A, then every polynomial in the ideal goes to 0, and those polynomials generate an ideal. Two very important properties regarding ideals and their varieties are the strong Nullsensatz, which means that if the field where we define these objects is algebraically closed, then the radical of an ideal is equal to its ideal's variety's ideal. What a radical ideal is that, for example, if you have an ideal generated with x minus 1 squared, then its radical is x minus 1, which means you cancel the multiplicities of the solutions. And if K is algebraically closed, then if you take a variety to an ideal, it is equal to its radical. And if you take a radical to a variety, it is equal to its variety. These maps are inclusion reversing bijections and inverses of each other. Inclusion reversing means that if you take a variety of intersection of two ideals, it equals to the union of the varieties of the two ideals. And an important theorem which I will use in the last part, please remember this, is that if G is a Gröbner basis for I, then the number of monomials that are not divisible by any of the leading terms of G is equal to the number of points in the variety, with multiplicities. Then if you don't have multiplicities, then the monomials are equal to the numbers in variety. So one last thing which I will use is the saturation. A saturation is definition is as follows, but in the level of varieties, what it means that when you take variety of J and variety of I and variety of J, then variety of the saturation corresponds to taking out the variety of J from the variety of I and taking its closure. Why do we take its closure? Because we want varieties to be closed. And when you take out a set from another set, it may not be closed, so we take its closure. So for the parameter continuation theorem, it is mainly used in the polynomial homotopy. Polynomial homotopy is that, let's say you want to solve this polynomial system F with n polynomials and n variables because we want the system to be square. And this is a really complex problem. Then you start with another system, G, where you know all the solutions. And using homotopy, you slightly deform solutions of G and G itself towards the solutions of F and F itself. But when you use this deformation, you want that for every 0 in G, there is a 0 in F. So along the solution path, you must not lose any of the zeros. So what parametric continuation theorem tells us that there exists a path, and here is the definition. Let F be a family of polynomial systems which do not have fixed parameters, and let Q be a point in the parameter space. Then we say NQ equals to the number of regular zeros in the polynomial system. Then the number of regular zeros are finite, and there exists a subvariety which has lower dimension than CK, called discriminant, such that all the NQs are equal. And Q is not in the discriminant. What the idea of the proof is to show that this discriminant has at least one dimension lower than CK, and since the complex space is even dimensional, it has in the dimension says 2 dimension lower. So this space is path connected. So there exists a path where we can take G to F. So for an example, assume this simple quadratic polynomial and its discriminant. Then in the complex space, it has 2 solutions, and the discriminant is an hypersurface. The solution of discriminant is a hypersurface. Then since C2 is 4-dimensional and the discriminant is 2-dimensional, you can avoid the discriminant and take this equation to any equation where you know the solutions. But however, in our look at this graph where the parabola is the solution of the discriminant, then in the upper plane, you have 2 solutions. In the lower plane, you have no solutions. And on the parabola, you only have 1 solution, which is in the discriminant. So you can take a path from the upper plane to the lower plane. So what this means that the theorem does not hold for non-algebraically closed spaces. So here is an outline of the proof. Let I be the ideal generated by the polynomial set, and let J be the ideal generated by the Jacobian determinant. And recall that the point is a regular 0 if the Jacobian determinant does not vanish. So then we define a map phi q which fixes the set parameters. For example, if phi q fxp equals to fxq, q is fixed. Then consider the ideals where we fix all the parameters in I and j. Then we take its saturation, which corresponds to removing solutions of j from the solutions of I. Then, as I explained, this means that we take the points where j does not vanish and I vanishes. So since the Jacobian determinant does not vanish, these are the regular zeros. Then by the definition of n cubed from the theorem, the number of points in the variety of the saturation does equal to the number of regular zeros. And we need to show that this number remains the same for general Q, which is not in the discriminant. So here is the main lemma, which is proposed in Brading and Borowick's recent paper, which use only Gröbner basis and varieties for the proof of the theorem. So lemma is here, but what it says that let G be a Gröbner basis for the saturation. Then there exists a subvariety, which is lower dimensional than the parameter space. And for all Qs which are not in the discriminant, phi qg is still a Gröbner basis for IQ, and none of the leading terms vanish when evaluated at Q. In particular, this equality holds. This lemma implies that since none of the leading terms vanish, then none of the non-leading terms which have lesser order than the leading terms vanish. Since then in the theorem, in the varieties, as I explained, this does equal to the number of points in the variety, which we call monomials under the staircase. Then for general Q, since those monomials do not vanish, we have same points for all Qs. For an example of the lemma, this is the standard quadratic polynomial, and it's generated by this ideal, and it is Jacobian determinant is this. Then if you calculate the Gröbner basis for the saturation, it is here, this set. Then let's take 2 points, one from the discriminant and one not. Then the lemma entails us that G does equal to the fixing of those points A, B, C. But latter does not hold since it is from the discriminant. And when you plug these points to the ideals, then the saturation, both of these ideals have the same solutions. So thus the solution is the whole solution space. Then the saturation is the whole polynomial ring. So GQ, then the saturation is equal to this. And G, when you fix the points in G, this is not a Gröbner basis for it. So these are the references. Here is the paper and the two main books I read. Thank you.